Hello everyone, I'm Dr. Sina Shamekhi and this is lecture 5, blood pressure and sound, the fifth lecture of the Bioinstrumentation course. First of all, we need to talk about some definitions. Blood pressure, as you can see, determining an individual's blood pressure is a standard clinical measurement. Number of direct, or in other words, invasive and indirect non-invasive techniques are being used to measure blood pressure in the human. Blood pressure values in the various chambers of the heart and in the peripheral vascular system help the physician determine the functional integrity of the cardiovascular system. And also, fluctuations in pressure recorded over the frequency range of hearing are called sounds. We use these words in our lecture. And the sources of heart sounds are the vibrations set up by the acceleration and deceleration of blood. In this slide, we have shown the blood circulation. The function of the blood circulation is to transport oxygen and other nutrients to the tissues of the body and to carry metabolic waste products away from the cells. The transportation is made possible by a pressurized vessel system, including the also consists of the arteries, veins, arteries, venules, and capillaries. As you can see here, we have some pressurized connected chambers, connected vessels used to transport oxygen. And oxygen is the most important material we need to continue our life. In this slide, the normal range of blood pressure inside various chambers of a normal heart have been shown. And this is only for you knowledge. I want you to be aware about the highest and lowest values and the role of the chambers inside the heart from the perspective of the blood pressure. It is important to know the left ventricle and the arterial have the highest values of blood pressure, and also the right atrium and the right ventricle have the lowest values of the blood pressure inside our heart and connected vessels inside our heart. In this slide, some critical regions of blood pressure and related problems, related disease have been shown, and this is only for your knowledge. As an engineer, as a biomedical engineer, you should be aware about some ranges of blood pressure to use it as your basic information. And in this slide, the form of the pressure and also the value of the pressure inside our vessel have been shown. As you can see, the highest level of blood pressure is in the arteries, and the lowest range is in veins. And as you can see, the pressure inside the arteries by here, all these vessels are arteries, have a waveform of pulsatile waveform, and as you can see, the pressure decreases from the arteries to the vein, and inside the capillaries, and at the border, at the left side is the artery capillaries, and at the right side the venous capillaries. As you can see, the pulsation inside the vessels decreases, and the pulsation is vanished, is disappeared at this border, and the blood flow inside the veins is not a pulsatile flow, pulsatile form. And also we should be aware about the values, because we are engineers and we should be able to design a correct and appropriate the device to measure pressure inside various vessels inside our vascular system, cardiovascular system. Therefore, we should be aware about the pressure range, and we should be able to use correct devices to record these pressures. Blood pressure is an important measure of the state of the heart and blood vessels. It is defined as the force the blood exerts against the blood vessel walls. The pumping action of the heart generates a blood flow through the vessels. When this flow is met by resistance from vessel walls, blood pressure results. Vessel walls also some other types of resistance, such as orifices. Orifices inside, for example, our heart will change the blood pressure. Therefore, all parts of the cardiovascular systems contribute to vary, to change the pressure inside various parts of this cardiovascular system, cardiovascular connected system. Year 1733 was the most important year in the world of blood pressure measurement. In that year, Stefan Hals and his assistant, by using a simple reed inserted inside the vessel of the neck of a horse, they measure the blood pressure inside the cardiovascular system of this horse. They saw that the blood rises inside this reed up to a specific height, as you can see here. And as you can see, this is a simple but the basic method approach to measure the blood pressure. We cannot use this method as a routine, as a common method, but this approach was the basic principle for fabrication nowadays mercury pressure measurement systems. Because of using mercury, because the mercury is heavier than blood and also water, the height of the mercury inside the column will smaller than blood, and we can use it inside our routine measuring tasks. We have two main approaches to blood pressure measurement. The first one is the direct measurement. The direct measurement truly measure the pressure inside the vessel using some catheter. And the second one is the indirect measurement using sound or vibration on the skin surface to monitor, in other words, to guess the systolic pressure and diastolic pressure. For example, auscultatory method, oscillometric method, and so on. And also the actual pressure sensor can be strain gauge, variable inductance, variable capacitance, optoelectronic sensors, and also piezoelectric, and also other types of sensors can be used in actual pressure sensing for blood pressure measurement. In this lecture, direct measurement means invasive measurement. Not in all concepts of biomedical engineering, but in this lecture we can use invasive measurement instead of direct measurement. And as you can see, in direct method, a vessel is punctured and a catheter is guided inside the vessel. The most common sites are brachial and radial arteries, but also other sites can be used. For example, femoral artery, as you can see in this. This is radial site, this is brachial site, and this one is femoral artery site. Direct blood pressure sensor systems can be divided into two general categories, extravascular and intravascular sensor systems. Extravascular means that the measuring site is inside the vessel, but the sensor is outside the vessel. And intravascular means that both of the measuring and the sensor site are inside the vessel. This method is precise, but it is also a complex procedure involving many risks, because we puncture the vessel, and the artery vessels have high values of pressure, and there is many risks using these types of blood pressure measurement. Also, we should emphasize that we will use only when essential to determine the blood pressure continuously and accurately in dynamic circumstances. In this slide, extravascular sensor in general is explained. Extravascular pressure system consists of a catheter, couples a flush solution through a disposable pressure sensor with an integral flush device to the sensing port. The three-way stopcock is used to take blood samples and zero the pressure sensor. Let's review. A catheter, this is the catheter, inserted inside the body, inside the vessel, and as you can see, as we mentioned before, extravascular here. The sensing device, the sensor, is located outside the body, but the sensing main site is inside the body. Extravascular direct pressure sensing method. And this system couples a flush solution. The flush solution is inside in this bag, and using some pressure controlling system, we will calibrate the pressure inside the connected pipe system inside our transducer, our sensing element, and also the piping system. Okay. The sensor is located behind the catheter, and the vascular pressure is transmitted via this liquid-filled catheter. This catheter is full of some liquid. The pressure will be transferred. This is the blood, and this is the catheter. This is the vessel. We have blood here. The pressure of the blood will transfer by the liquid inside this catheter. The pressure will be transferred by this liquid inside this catheter to the sensing transducer. The advantage of the system is its stability, and because of the frequency response of the system, we have some limitation in detecting, especially in higher frequencies, because some hydraulic properties of the system, including the liquid-filled catheter, the solution, and also the piping system, the wall of the piping system will affect the frequency response of the system. And in particular, we have a low pass filter in all of these extravascular catheter-based liquid-filled catheter systems. And also, as you can see, as we talked before in in the lecture of the sensors, we talk about some parts, sensing element and transducer, the signal conditioning, sensing element and signal conditioning, two main parts of the transducer. As you can see, the sensing element is the catheter here, and we have a signal conditioning parts here, which will convert the movement of the liquid inside the catheter to some electric output. This is electric connector, and we have some electric output here generated by this transducer, and we can connect the sensor to some amplifier to measure the blood pressure. This is another presentation of the extravascular direct method. As you can see, catheter connected to a pressure sensor through three-way stopcock. The system is filled with saline heparin solution. Heparin is used to have an anticoagulant agent and must be flushed every few minutes. Catheter inserted through surgical cut down or percutaneous insertion. Blood pressure info is transmitted via the catheter liquid to the sensor diaphragm. And also you should answer this question: why we use water but not air? The answer is the compression coefficient of the air is not appropriate for our measuring, and also the air is not compatible with our blood. It's dangerous. It's dangerous for insertion air inside our blood. We have many risks using blood inside some catheter inserted inside the vessel. Extravascular pressure sensor consists of two main parts. The first one is the reusable part. As you can see, this part is the reusable part of the sensor, and this part is an other connected catheter and piping parts, is some parts of a sensor which we should exchange it per recordings. The reusable parts, as you can see, consist of a diaphragm and some other electronic parts. A thin, flexible metal diaphragm is stretched across the opening of the transducer top, and also the diaphragm is connected to an inductive bridge, as we mentioned before in lecture 2 sensor. And as you can remember, we can use resistive bridges, Watson bridges, inductive bridges, strain gauges, and other types of displacement measuring, which flexes the strain gauge an amount proportional to the applied pressure. And also the disposable part of the sensor consists of a clear plastic dome filled with the fluid sits on the diaphragm. Here, as you can see here, this is the pressure dome connected to the reusable main parts of the sensor and provides the hydraulic coupling connected to the catheter and electrical connector typically houses the bridge circuit. This is a typical schematic and also real sensors, real extravascular sensors. And also we should use new catheter piping and plastic dome parts for each patients, but we can use reusable parts without any change. The routine disinfection should be utilized, but this part of the sensor can be used for many years. We have mentioned this system, this strain gauge based pressure sensor before, a lecture sensor. Therefore, we will not mention it again, but you can remember it. You can go back to that page and read it and remember the discussion and also the bridge, the Watson bridge we use for our better sensitivity and better measuring aims, and also the strain gauge inside the pressure. Remember it, read it and remember it. And I don't want to mention it again. In some